Hello, hello, hello. Welcome back. It is Thursday, 27th of November. I can see, we've already got 3 people in the chat. Wonderful news. So today, bit more interview prep. I'm thinking we've got this week and we've got next week. And I imagine most of you have got your interviews that week of the 8th to the 12th. So I'm going to kind of try and wrap things up this week and next week, and then maybe the week after do a bit of a debrief. Now, a lot of the stuff we've been doing has been very intense. So lots of that like intense graph sketching, intense derivation work, the developed stuff, the really out there questions. And so today, I think I wanted to take things back a little bit, bring it back to the syllabus, because I think I've given you time to digest those skills. And I think what's really important is to have a no regret strategy, right? So you want to go in, show your best work, and make sure you leave nothing on the table. Realistically, if you get asked a question that's a really difficult problem to solve, and you don't get to the end on that, you're not going to feel too bad about that. So I kind of had that in my graph sketching, where I didn't quite work out exactly what the behavior was going to be around the asymptotes in one of the really complicated graphs. Didn't feel too bad about that because I'd shown a lot of good work on the way. What is going to fill you with regret and what is going to make you kick yourself is if you fail on something you think you should know. Something from the syllabus where you're like, oh, god damn it, no, that equation's in the formula book, and like, it's in the ESAT spec, and why can't quite remember it. That's the kind of stuff that really gets to people. So as we move closer to the end, let's sort of bring things down a notch, kind of bring it back to basics, and just make sure you have your core stuff really established. Now, because we have people in the chat, I will also take suggestions. So that was one thing that I found really fun last week, is when you guys just like lobbed me random questions, and then I can demonstrate the problem-solving process live, unseen. Put myself really in your position so you can see how to handle that yourself. But with that in mind, I think let's just pop into it. There was one graph that was recommended in a comment, so I'm going to start there. But before I start there, I need to actually get the whiteboard up, don't I? Oops, apologies for that. While we're waiting, you guys can let me know when your interviews actually are, because that might be useful information. And whether you're going, and also just out of curiosity, whether you guys are going for natural sciences or engineering, because I'm curious to see what that blend is. Okay. So got the whiteboard good and ready. Let's get the screen shared. 9th of December for engineering. Cool. December 12th, NatSci. Oh, before I start sharing my screen then, speaking of NatSci, one of the things I'm going to do next week is also do a little bit of chemistry just for right at the end. Obviously, the engineering is just the math and the physics, but your NatSci is definitely going to have some, well, not definitely, but is likely to have some chemistry as well if you're doing that for A-level. So make sure that's part of your mix. Anything in the ESAT spec, make sure you're good and ready. Also, things that are really examinable, well, good for interview are, what's the word? Word is gone. Mechanisms, organic mechanisms. And maybe some of the tie-ins with like collision theory, because that's very similar to gas laws. So just make sure you're up on that, because I'm not doing that as much with the streaming. 11th of December for economics. Cool. So imagine lots of graph sketching there. I do a bit of economics. It's not something I'm like a super expert in, but I think a lot of that problem-solving process is still there. And actually, fun story about economics. In the end of my second year, I got a research placement at Caltech, where Cambridge sent 2 people from, I think it was 5 different colleges. So we were a cohort of 10 going out to California. And I remember we had at least one economist there. So they do economics at Caltech. So they do very much kind of lump it in with the sciences. And when I saw the papers he was reading, it's just pure math. So yeah, when you get up there, it's like quite intense economics, isn't it? So let's get into it. As always, if you want to lob in a question, feel free. But in the meantime, the recommended graph, and I haven't seen this yet, is y equals, nope, already got that wrong. It was equal to x cubed e to the minus x. So the first thing I'm going to do is draw my component graphs. So I know what x cubed looks like. It does that. It goes to 0. It comes up again, roughly speaking. I know what e to the minus x does. It's going to go something like that. Where that's going through 1, that's going through 0. And so I can see there's going to be an interesting thing happening here. Well, first of all, let's think about intersections. I can see that when x equals 0, y equals 0. So I know it's going to go through the origin. I would also expect that to be the only intersection point. I can see that when x is positive, both of these graphs are positive, and positive times positive is positive. I can see that when x is negative, I have a negative times a positive, which will be a negative. I can also see that as we tend to negative infinity, I know it's negative, but also the magnitude is going to be very large because we're having a very large magnitude number multiplied by a very large magnitude number. So it's going to be going off to minus infinity. I know it goes through 0. So then the question becomes, well, actually, the question becomes what happens here? Which dominates? Is the tending to infinity going to dominate, or is the tending to 0 going to dominate when I multiply them? A good, quick, and easy way to see this would be if there's any turning points. So let me get that first. First d second plus second d first. Let's factorize out an x squared e to the minus x. Ooh, this is not relevant to the session, unfortunately. Hoping you could help some people with a query I have about personal statements. Yes, Edward, I will absolutely do that. Let me just knock this graph out, and then we'll get right to it. So this would be 3 minus x. So I know that there will be stationary points. E to the minus x will never be 0. There will be stationary points when x equals 0 and when x equals 3. Interesting. So we do have a turning point when x equals 3. When x equals 3, y is equal to 27 e to the minus 3. So that's a relevant point. And that automatically implies, well, if I take a second derivative, okay, let me tell you what, so let me lead with intuition first. So intuition is telling me at this point, it's not going to have a turning point and then go shooting off to infinity. It's going to be tending probably to 0. And what I also know from my exponential is exponentials tend to dominate. So they tend to decay much more quickly than polynomials. So I know e to the x definitely outperforms x cubed. And, okay, on that basis, let me rewrite that. So y is equal to x cubed over e to the x. And on the basis of exactly what I just said, as x tends to infinity, the e to the x will be much bigger than the x cubed based on the Taylor expansion. So I know the e to the x is going to win and that it will tend to 0. So I would expect the graph to do something like this. I would expect it to have a turning point here, come up, turn around, and come back again. And so that is the graph, as I see it, where that is the point 3 and, what did I say, 27 e to the minus q, e to the minus 3. If I wanted to be extra certain about that, I would also take the second derivative and demonstrate that the second derivative is negative. Okay, question time. So teachers said that my personal statement needed to have more of me in it, not just mathematical physics, and my interest for studying it in university, which didn't make any sense to me. I'm not sure I agree with your teacher on that. Well, it depends on what you mean by more of you. Where sometimes I think a personal, okay, let's have that conversation. So I think a personal, because also a personal statement can come up in interview, especially if you have imperial as well. In my book, a personal statement should do 2 things. It should demonstrate true intrinsic interest, and it should show that you have the conscientiousness to turn that interest into action. So a statement should say, I found out about this idea and it kind of sparked a fascination because of XYZ. And so I read about this. Oh, and then I did this research project. And the ability to explain what you've learned and to explain what you did shows that you went through the steps to really give yourself a new understanding that you didn't have before. And the reason why that's good is because it shows what they're looking for in interview, which is the ability to independently learn and get yourself from point A to point B without someone needing to drag you along the process. So with that said, I suppose it depends on how you've spoken about your mathematical physics. If it's just saying these things happen, it maybe what they're saying is they're not getting a sense of conscientiousness in terms of I did this, I did that. If they mean like, oh, I like these things and I have these hobbies, then I would disagree. So it's kind of a matter of what exactly you mean by that. But as we're talking about personal statements, what I will say is any technical term that you include or any specific project that you include, you're kind of inviting it. You're like, okay, get me here. This is sort of home ground for me where I'm nice and confident and I should be able to talk about this. So anything you've mentioned in your personal statement, make sure you're conversational in, can explain all the concepts and how everything links up. So all that being said, I don't necessarily agree with what your teacher said. I think having a very content-focused personal statement is not a bad thing, as long as you're conversational in it and can actually explain all the concepts. Feel free to let me know if that didn't answer your question. But in the meantime, I think we're going to do a bunch of more syllabus-based physicsy things. So certain things that you want to make sure you're not getting wrong. So one thing, for instance, could be, let's consider, this could be fun. And in fact, it would be even more fun if you could see what I was doing. Ooh, follow-up comment. Yes, I did that and spoke about my interest between the link of using mathematics to describe physical systems and talked about a question I had and how I solved that through super curriculars. Yeah, I don't see any issue. And besides, I'd also, by the way, while we're here, especially if you're going for Oxbridge, the personal statement is probably the least most important part because you also get your supplemental questionnaire and you have your ESAT/PAT test and you have your interview. So I'd rank it like interview, entrance test, personal statement. So I wouldn't worry too much. Like I said in my interview, it felt like they hadn't even read it. Said it needs to be more about you. I would say personal statement, you get a lot of conflicting guidance. And I actually think a lot of, as I advise people to do really technical stuff. So from what you're saying, I don't see any red flags in what you did with your personal statement. Okay, now let me share my screen and let's get into the mechanic things. So let's say I have an object being dropped off a sort of cliff or shelf or table of height h at exactly the same time that another object is projected up with speed u from the ground. Let's derive an expression for the place where they collide as a function of u. Perfect. No worries, Edward. And what I will say, by the way, is the people you're competing against have very technical personal statements. So you're probably on a level with them. Like you do want it to be quite engaged to show, because that is personal. It shows them what you're able to engage with intellectually and your ability to explain it. Like it shows a POV. Like you're talking about that specific equation and not others because you're interested in it. Yeah, don't worry. So here, okay, let's consider particle A, particle B. Reason why I'm picking SUVAT, commonly tested in interview and commonly misunderstood because of the vector nature of all of the bits to it. Especially something like this where it's simultaneous SUVAT, there's loads of opportunity to make mistakes. So let's consider this to be point C. I like to talk about events and episodes. So let's consider A going to C. And we can consider B going to C separately. Laying things out with a good diagram and nice systematic method shows good problem-solving skills. Honestly, I'll just do that as I go. Right, so we know this is projectile motion, so it's going to be minus g in both directions. I'm going to choose upwards as being positive as my sign convention, even though A is falling downwards, and a lot of people would want to call downwards positive for A. Because this is simultaneous, I want to keep in the same sort of frame of reference here, not in the sort of technical sense of reference frame for physics. Anyway, A going to C. The acceleration is minus g. This one's being dropped, so the speed is 0. S, let's not call it S. I want this to be x, the height at which they collide. So I'll define it that way. Now that distance here I know is going to be big H minus x, but I know that that displacement is downwards. It's a vector, it's negative of that, so it should be x minus big H. And this is time t. This will be time t, u equals u. And I know that these collide at the same time. So I know that s equals ut plus half at squared. I'll just lay out the SUVAT equation again, just to calm myself down, show them I know what I'm talking about, that I can be nice and systematic. It's always good to quote your starting equations as well, so that you sort of show your sort of intellectual authority for your argument, rather than launch straight in. S equals ut minus a half gt squared. Cool. But then we'll need to eliminate for t. So from this one, s equals ut is 0 minus a half g, I'll call it big T actually. So the time at which they collide, maybe I have to solve for that and then plug it in. I suppose we can get t in terms of h. Would have helped if I'd done this beforehand. Maybe it's not as simple as I thought. So what is the height? We want to find x in terms of u. How am I going to do this? I know I want to eliminate time. So why don't I say that, well, the half gt squared is easy. So that's u big T plus x minus h. Which is unhelpful because then that cancels. But maybe that's not unhelpful because then h over u, here we go, is equal to t. And I could plug that in here maybe and say that x is equal to h minus a half gt squared. Let me just check that this tracks. Yep. Okay, so just making sure I've dotted all my I's and crossed all my T's here. Does this make sense as an expression? So I suppose we can get it in terms of h. 1 minus gh. I suppose I didn't want it to have an h in here as well. I really wanted it to be sort of like linear in h. But I suppose h will matter. H will matter because, again, it does affect the time. And do the units work out? That's an acceleration times a distance all over speed squared, which is speed squared over speed squared. So yeah, this is unitless. So this does work. This is a fraction of h. And so I think I've done that now. What meaning can I get from this? So here, I'm thinking that is interesting. The fact that h is equal to ut is interesting to me because distance equals speed times time. That is distance h, speed u time t. So it's almost, and actually this does kind of make sense because from their perspective, so relative to A, because they are both accelerating the same way, it's almost like weightlessness. So they're kind of doing if you imagine sort of cars on the road, if the car to your right is moving faster than you, it looks like it's moving ahead of you with this relative speed. And similarly here, because they're both accelerating with each other, because they're accelerating with each other, the only thing sort of comparing them, I'm not explaining this very well, but there's a relative speed of u between them, and so the time at which they meet, if you imagine being at A's perspective, from A's perspective, you're both accelerating in the same way. So it's almost exactly the same as if you were on the same train and the train had a constant acceleration. But within the train, you looking at particle B is just moving towards you with a speed u, and so clearly h, the distance between you, equals that relative speed u times time t, and then you collide. So actually this does kind of make sense, but it's interesting that it sort of ignores the acceleration because they accelerate together. So that's something of meaning. And then here, I don't think it's meaningful to combine those into a single fraction. But what I can predict is how that varies with u. So x as a function of u, g is fixed, h is fixed. As u increases, well, as u tends to infinity, that tends to 0 and x tends to h, which makes sense because a doesn't have any time to drop, u just hits it. And as u tends to 0, well, that blows up. No. As u tends to 0, x would tend to infinity. That doesn't make sense. So that predicts something unphysical. Ooh, okay. Because let me start by what I understand physically. I clearly know from real world, if u is 0, then x should be 0. Because that's not moving, and so the height at which they collide is there at the bottom. So why is that not coming out? Interesting. Am I missing something? I'm probably missing something. Oh, no, wait, hold on a minute. No. Oh, sorry. Oh my God, that's so clever. Okay, I just understood the physical significance of u equals 0. Yes. Okay, so here, it is true that as u tends to 0, this thing will blow up, and it will be big compared to 1, which means this is minus gh over 2u squared, and as that goes shooting off to infinity, the x will tend to minus infinity. Now, why is that important? Because if you think about what that means physically, a is dropped from, has no speed. U has no speed. They would both just be released from 0, and they would just accelerate but never meet, because they would just be there and then just both keep accelerating. So they would never hit each other. What this is the missing here is the fact that this model does not take into account the fact that there is a ground. So realistically, x cannot go below 0. The reason why they would collide at 0 is not based on the mathematical model, but based on the physical constraints of the world, the fact that x cannot go less than 0. So once b is at 0, which it already is, and can't go any lower, it stops, and then a is allowed to catch up. That's clever. Okay, so I'm satisfied with that. Gonna look at comments again. Here, physical NatSci. My interviewers are teach math and physics. I hope we don't get any chemistry. Do not bank on that. If you are applying, in fact, let's have a little bit of commentary between each question. So feel free to drop your questions between each question. I'll make sure to get to them. So if you are going for Phys NatSci, first of all, what would be relevant is if you are doing chemistry A level, because I have in fact, one of my best friends from university who I lived with for 3 of the 4 years I was there. He got in for physical natural sciences having done no chemistry A level. If you haven't done chemistry A level, they are not going to ask you any chemistry. If you are doing chemistry A level, they are likely to ask you some chemistry on the basis that you are likely to do it as one of your options for natural sciences. If you've indicated, for instance, that you expressly want to do in your supplemental questionnaire physics and material science and earth science, and you have explicitly said, I don't want to do chemistry, then you're probably safe. But if you haven't done that, the default will be to check your chemistry is okay. So just, and I've had this conversation with someone in the past where I said I would expect the interview to be predominantly physics, but it may include it. I can't guarantee it won't include some chemistry. He goes in, they ask him a mechanism, he falls apart. So you can't guarantee it. Your interview is the founder of Isaac Physics. That's awesome. Funny that I mentioned I've done many questions on Isaac Physics when I've only done 50 questions in a time span of 6 months. I consider that a lot of questions. It's more questions than I've done. I don't do Isaac Physics, but I have heard of it. If you said that in your personal statement, he might add that you could. I mean, let's be real. He's not going to ask and sort of compliment me on Isaac Physics, but you could talk about a particular question you found interesting and why. But do definitely check on your chemistry. Just a Bean says, I have a question on differential equations. If there were a question involving them and they asked me what it represented, how would I go about this? Interesting. How would you go about this? I suppose you could think about what the things mean physically. So for instance, let me take an example. So I'll do so let's consider Newton's cooling equation. So in this one, this is saying that, hold on, let me just take a bit of water. This is saying that the rate of cooling or the rate of heating is proportional to the temperature difference with the surroundings. And in this case, you could solve this, it would give you an exponential. But the way to think about that is what this physically means. This means the rate of change of temperature, and this is the sort of temperature difference. So you can kind of interpret it from that perspective. You could get differential equations that look something like this. So this is a classic. I think it's and now this at first sight looks bad when it was plus y. But then when you move that across to the other side, you'll realize that the second differential is equal to the negative of y. But hang on a minute, what does this remind you of? This reminds you of acceleration is proportional to minus x. And this ends up being simple harmonic motion. So I would say they're never going to ask you something completely out of the blue. They are either going to ask you a differential equation that in some way relates to the syllabus, or it's going to be sufficiently close to the syllabus that you can piece it together on the spot, if that makes sense. Or third option, using just your pure math skills, you could just blindly solve it and then interpret the result rather than the equation. So you can get this, for instance, another classic differential equation would be for exponential decay, the number dn dt equals minus lambda n for exponential decay. You can solve that. So integral of 1 over n between, I don't know, 0 and n dn equals integral from 0 to t of minus lambda dt. So ln n, you can't really do from 0, can you, on that? No, but you can do from n naught. So you start at n naught and you end up on n. So this becomes ln n minus ln n naught equals minus lambda t. Actually, let me do this. Let me not skip steps. For n and n naught, minus lambda t between t and 0, because and the reason why these limits are chosen, because at t equals 0, n equals n naught. So we get ln n minus ln n naught equals minus lambda t, which means that ln of n over n naught equals minus lambda t. And then from there, you know the rest, n equals n naught e to the minus lambda t, which gives you that equation that you're familiar with. So yeah, so one of those three things. Either inspect it just in its own right, what terms are included, or relate it to the syllabus, or solve and interpret if you get differential equations. Very welcome. So let's go. Let's do some electricity stuff. So let's consider case. I've already done this wrong. So this is adapted, and by adapted, I mean paraphrase, because I can't remember the exact question from a PAT test, I think, where we're going to have two loops, and we're actually going to have two cells, where this one's going to be 12-volt battery, this one's going to be a 10-volt battery. We're first going to consider, question. Sorry, what was that? Newton's law of cooling. Newton's law of cooling says that the rate of thermal temperature decrease is proportional. So for instance, if I have a cup of coffee and we're considering temperature against time for the coffee, it's going to start off at the temperature it is, and it's going to slowly reach room temperature, kind of decaying away. If that's room temperature. And the reason why it has that exponential decay shape is because of this equation. Delta T over T is proportional to this temperature differential. And you'll notice, by the way, that's similar to the equation you had on the ESAT. Rate of thermal energy transfer is equal to Ka times the temperature gradient, which is another differential equation that theoretically could come up. Although this is less syllabus, they'd probably have to do this learning on the spot. Would that work if a cold drink were put in a hot room? Yes. Although in that case, you can imagine from like real world understanding, when you solve that differential equation, and I will leave that as an exercise to you because it's very fun, it should look something like this, which is of the form of a 1 minus e to the minus t type of curve. So yes, it works both ways. Now, coming back down here for this electricity question. Let's consider first, just to warm up to this question, the situation where the resistance here is set to 0. So the question is, what is the voltage now on this battery? The reason why I bring this up now is because Kirchoff's laws are in the syllabus and could be a real kick yourself moment. For the first question, it was SUVAT-y things, especially the vector nature, making sure that things are positive or negative. That could really trip people up. For circuits, things that can really trip people up are Kirchoff's laws in parallel, understanding these complicated scenarios. So here, what you're looking at is, well, let's remind ourselves Kirchoff's laws. The first law says that at any junction, current in equals current out, which people intuitively really understand. And what people forget about is the second law, which is that in any closed loop, strictly speaking, the sum of the potential differences is 0. I prefer to think of that practically as in any closed loop, voltage gained equals voltage lost. So here, if this resistance is set to 0, this loop makes a whole lot more sense, because in this loop, the voltage gained is 12, so the voltage lost has to be 12. And the only resistor at which to do that is this one. So that has to be 12 volts. And I'm conscious that I put these batteries the wrong way around. So that's meant to be the 10, that's meant to be the 12. So this one becomes 10. And then in this loop, again, voltage gained equals voltage lost. And so this becomes 2 volts. Now, strictly speaking, what I just did was not correct in that I didn't consider the direction of the current when considering my loops. So what I should have done is, we know that these cells will drive current out of them in this direction. And so we can follow that up. So we know the current is doing that. So the current must be coming down through here, going around like that. And now that I know this, I can draw the loop in this direction, and I can draw the loop in this direction, and everything I did works. Here, I'm going with the arrows, and so everything is as expected. Voltage gain, 10, voltage drop, 10. And same thing here. It gets a bit more interesting if you consider the overall loop around the outside. And in that case, let's consider going around in that direction. When you're going against the flow of current, the signs flip. So here, the voltage gain here, you would sort of gain 12, lose 2, gain 0, lose 10. So instead of losing at a resistor, going the wrong way through it, you would gain, and going the wrong way through a cell, you would lose. So going around the outside, the overall gain in potential difference from the EMFs is 2. So the overall loss has to be 2, which is why this becomes 2 volts as well. Now, we can consider a more complicated scenario of what happens as I slowly begin to increase that resistance. And in that case, you will get a V here for whatever V that is. If a certain voltage is, if there's a certain potential difference across the variable resistor, speaking in proper technical language now, then we know the potential difference across this resistor must be 10 minus V. And we know the voltages in this loop must sum to 12, because that's the voltage gain. And so this becomes 2 plus V. In other words, no matter what I set this resistor to, this resistor will be 2 volts more, which is exactly the same as the difference in the EMFs, which I think is quite interesting. If anyone has any more electronics questions, feel free to drop those in. What could I test? I mean, everyone knows about resistors in parallel and in series. I think potential dividers could be interesting. Rearranging equations could be good. In the interest of time, though, I'm tempted to move on. We can always come back to that if you want to do a bit more electricity work. I have a decent amount of DC circuit questions. Nice. But yeah, in terms of resources as well, you obviously have your Isaac Physics, you have your Physics Olympiad. And to be honest, ChatGPT is not the worst at sort of prompting you with possible questions. So just testing your skills and making sure you're handling a variety of situations. And I've also covered some other circuit questions I know in previous interview streams that I've done. Ooh, you're in a program called Compos by Oxford. Compos, C-O-M-P-O-S. So maybe worth looking into if you want a bit of last-minute challenge from them. Moving on to waves now, because I feel like I haven't done as much of that as I should have. Let me ask the question. When you look at a puddle on the side of the road, Oh, didn't get an interview. Oh, I'm sorry about that, man. It sucks. But actually, do you know what? Now is the perfect time to have this conversation. Didn't get an interview. Do not apologize to me. Here's what I will say about that. Whatever Oxbridge says to you, you say thank you. And here's why. If you get an interview, if you get an offer, you say thank you. This is going to be a great opportunity. If you don't get one, then you say thank you, because what they would have done to you, you would not have enjoyed. Because again, it's a very, very specific style of learning, and it really isn't for everyone, including some of the people who get in, by the way. Like, you can often tell the people, and by the way, just because you don't get in for undergrad doesn't mean you can't get in later. Like, there's a lot of people who transfer in post-grad. So a lot of people get like a master's, and that's always an available path to you. And usually when you can tell the difference between postgrads who did their undergrad at Cambridge and those who didn't, because the ones who came from the outside are often just a little bit better adjusted because the undergrad could just be like very, very intense. And I'll say, just in terms of confidence, wherever you go, being around the top third of your cohort is just really good to give you a sense of feeling really, competent and capable. So a lot of the times as well, people come in, if you come into Cambridge and you're kind of like feeling at the bottom, you don't feel very good about yourself and your capabilities. And so what I think is important is to come at this with a no regret strategy. You've put in a bid for how much work you're willing to do to keep yourself psychologically stable. And if that level of work is not enough to get by in Cambridge, then Cambridge is not where you want to be. Because let's say theoretically you could have worked yourself 8 hours a day for a month to get really, really good at the ESAT and the interview skills, and you just about squeak in. That is the amount of effort that would be required to just about keep afloat. And so what you did was you put in exactly the right amount of effort for you at the level you're at right now, and you offered it to them, and then they decided whether that would have been good for you to move through their system, and they've said not right now. So honestly, I would take no regrets from that and say thank you, because you don't know what it would have been like to move through the system, and they've probably helped you dodge a bullet. And wherever you go, you can focus on succeeding and pushing your way up to the sort of top of your year, getting a really good sort of social life, and just being the absolute best you can in every dimension, with a view of either then going into a profession on the other end of it, or if you did want to pivot into academia and stay in academia, you can always come in for postgrad. So do not feel bad about yourself in any respect. I must say, 100% agree. Mental health at Oxbridge seems rough. Do you know what it is? It's genuinely, it's like, because the way people talk, there's a big difference between people who haven't been to Oxbridge and people who have when it comes to the mental health side, or like the culture. Because people who haven't been to Oxbridge think, oh, it's full of super geniuses who are always peacocking and it's super competitive and everyone's trying to race to the top. No, no. When you're actually there, it's more like, everything's fine. Everything's fine. Everything's fine. I'm drowning. And people kind of have this sort of like frenetic, sort of very anxious energy, where there's this constant looming, oh my God, I have so much on, which is why I think it can lead to people not coming out with the best mental health outcomes if it is not suited to you, which is why they're so rigorous in their application process, because they do not want to do anything to you that is not good for you. So yes, keep to your life plan. And by the way, people like Oxbridge, it's fun if you're supposed to be there, but it really isn't the be all end all. Like, there are so many people who I know people who've gone to Oxbridge who are currently unemployed and just not doing anything. And there are people who go to a bunch of other universities and are thriving because they were near the top of their cohort. They found really interesting people and they start businesses, or they get into specific. So they go to Nottingham or Birmingham or wherever Boots is founded. And Boots, I think, is Nottingham. And you can kind of have links into that. Yeah, nothing for it. Aiming for Imperial. Imperial's great. London's great. By the way, that's another thing. You actually get people who get offers from both and reject Cambridge because they know their quality of life would be better in London. There are all sorts of things that feed into this process. And so I think people think of Oxbridge as the shiny city on the hill that everyone you must go into, and as soon as you get in, your life will be fixed. Not so. Don't make yourself a slave to Oxbridge. Decide on a university that's good for you. Get in there, do the best you can. Absolutely. Now, what we're doing here is we're still trying really hard because we want to have that no regret strategy. Everything I've just said only works if you feel like you've shown your best work and then they decided not to sort of bring you into the process. What you don't want is to come out thinking, oh God, no, if they had seen this, then maybe I should have been there. And the way to avoid that is by going through this process, sticking to the syllabus, and making sure you show the best of what you know you can do. So with that in mind, let's keep going. And I want to do a bit of wave stuff. So let's consider, okay, you are going about your sort of day-to-day life. You see a puddle on the side of the road. You look at it. Loving the support in the chat, by the way. Thank you to everyone sort of offering support, because it is not easy, and you're all going through. You're gladiators in the arena. I've been through it. I'm retired now, but yeah, y'all are doing your absolute best, and you're doing good work, and you got a lot of pressure on your shoulders, much more than I have at this point in my life. So keep at it. You're doing good stuff. So you've got your puddle. You've got a little bit of oil on top of the water. What do you see? I think from your day-to-day life, you kind of see a rainbow effect. You see a shimmering effect, and they say, okay, good. Why? Why do you see that optical effect? And this is a good chance to demonstrate what you know from the syllabus about interference. So what we know is that some of the light bounces off at the surface of the oil, which does not mix with the water. So we have the oil sitting on top of the water, and we get these two reflections. Now, from interference, you know that because the light has traveled different lengths through the oil, there is now a path difference between these two rays meeting at your eye. When that path difference is equal to a whole number of wavelengths, then you get constructive interference, and you see the light. When the path difference is n plus a half of lambda, we know we get destructive interference, and that wavelength of light does not get seen. If there was only one wavelength of light, then we would see a stripy pattern. We would see some places, because we're viewing different angles, which means because of the different viewing angle. So if that's viewing angle of theta with the normal, for instance, then that's reflected. Angle of incidence is angle of reflection. So that's kept going. That would also be theta. That would be theta. But the point here is you view it at different angles of theta, and that will affect this path difference. So the path difference has a dependence on theta. Does this depend on small angle? I don't think it does. We might be able to derive that, but let's do it qualitatively for now, because I think the derivation is outside the syllabus. But the point here is at different viewing angles, the path difference changes. And so there's some viewing angles where the path difference is a whole number of wavelengths. And so you would see the color. And as you move your angle, you would then see nothing. Then you would see a color again. So you would see these stripes. Now, when there is the white ambient light around you, when it has all the wavelengths in it, when you're looking at it, some of those wavelengths are the color that you see is the color which is being constructively interfered, where constructive interference is happening. And so you will see a range of colors because at the different viewing angles, different wavelengths will have this condition of n lambda being met for that particular path difference. And so that wavelength is the one that you see. And so the color changes and you see this rainbow effect. I think that's as far as I want to go in terms of like pure syllabus material for that particular question. Another question you could be asked, which is pure syllabus, would be to derive the equation for a diffraction grating. I don't know for certain that's in everyone's syllabus by this point, but it may be worth considering. Or we could do it. Is Young's double slit better? Now let's do diffraction grating. So let's consider a diffraction grating where we have a bunch of different slits going to a screen. Light comes into the diffraction grating, and then it goes to the screen. Let's consider a point here where all of the different beams are interfering constructively. Ooh, we got a question. May I ask how to speed up with solving problems? I like to ponder about Olympiad problems for a bit too long. That's a good point. And in fact, this is right at the start of the question. So let me take comments before I launch into the new one. That's a good question because it talks about what I would kind of consider level of scope. So there's two different types of student I see. There's the person who likes a top-down approach, where you see the big picture and then you drill down into the detail, versus someone who likes to start at the detail and then solve it very comprehensively. I'm more of a big picture guy. You can see that a lot where I kind of zoom out and think, well, what do I expect? Let me just stop thinking for a second. What's common sense here? And then dig into it. If you're taking it a bit too long, then it might be a case of spending too much time on detail, which isn't significant to the big picture. So if you feel like you want to, but I can see how it would be tempting to do that, to demonstrate everything you can do. Instead, yeah, you start with axiomatic thinking mostly. What you could consider doing is zooming out, telling the high level story first, and then they will ask specific questions about parts that they want to go into. So rather than solving everything in one go, by telling them everything that there is, you show that you could go somewhere else if time allowed. But then they kind of do a choose their own adventure through your brain. So let me think about, is there a way that yeah. So, and in fact, by the way, I am going to demonstrate that in my final interview question next Thursday. Well, it's the final interview session next Thursday. I'm holding off because I'm saving that. I love that question. And I'm using it for a lot of my mock interviews. Some of which are coming through from the channel, by the way. So I'm busy, but do have some space for like one-off mock interviews. So if you check the sort of description and the channel description, there's like a public-facing email you can email if you want to. But I'm saving some of my questions for that. And then next week, I'm just sort of going to dump everything to make sure it's all out there. But there's one question there where I'm going to demonstrate exactly what you're talking about. How much is the tutoring? So the truth there is that the rate varies. Yeah, that's reasonable. So rate varies as it should, because realistically tuition is not necessarily the most accessible for everyone. So you tend to offer a sliding scale depending on need. I'd say for short term, what I've been saying, yeah, I would say the short term work I've been offering at 65, which is, would it be possible to do an interview on live so people can watch and see how it goes? That I won't do because doing an interview with someone else, you get into the consent issues and they're minors, and because I'm new to this, I'm not gonna want to have to deal with all that. I also don't want to put them on blast. But also YouTube is full of different mock interviews you can watch. So feel free to get in touch if you want to get in touch about any sort of specific things. So I'm gonna show you how to do that. But the main thing to say about that in terms is start with the high level. these are all the topics that relate to this question. These are all the places I can go. I feel like I want to go down this path. So it shows breadth and then depth, as opposed to trying to solve everything all at once. Ooh, Tom Rock's Math recently did one for Cambridge Math. Nice. Cool. So let me get into this. Patrick casually saving my Cambridge application. Thank you very much. Here to help. So this is a question. The way to think about this, you have your diffraction grating. The diffraction grating is sending out different beams of light, which are meeting at different points. If we consider this point, where everything is constructive interference, then we know the different beams have a path difference of n lambda. Let's consider the first order where n equals 1. What that means is you have these different rays meeting at this point. And because it's at that angle, if I kind of zoom in on the different rays coming out of these two, if this is distance d, the difference between two slits, and this is angle theta, which is the same as the angle of the beam from the direct angle, from head on. So if that is theta, then that is also theta. Let me zoom in a bit. Then this bit here is the path difference. And we can see, if I zoom back out again, if I draw that triangle a bit bigger, if that's theta and that's d and that's the path difference, we can see that path difference is equal to d sine theta. But we know that that path difference has to be equal to n lambda. And so, bam, very quickly, we get the equation for diffraction gratings. So all this requires is a little bit of resolving triangle work and understanding how interference works. So we could be prime for asking questions. Then another question, by the way, might be how to compare what you see here with a double slit. So with double slit, you see these alternating bright and dark fringes with finite width. So the bright fringes have some width to them. Whereas here, you only get extremely specific beams at extremely specific points. Now, the reason why is because if we only have two slits, let's imagine moving a tiny bit off from perfect constructive interference. Then what happens is the path difference is not exactly n lambda, but they're not sufficiently out to completely cancel each other, so you still get some constructive interference there. Whereas here, let's imagine this is where we only move like sort of 1/20th off of that. So by what that I mean is, how exactly am I going to phrase this? So let's say the path difference now becomes just like lambda over 20. Well, the path difference between these two would be lambda over 20. Between all of them would be lambda over 20. So you would have lambda over 20, 2 lambda over 20, 3, 4, 5, 6, 7, 8, 9, 10. And then suddenly this one down here is 10 lambda over 20 out of phase, which is lambda over 2. These perfectly can destroy each other. That's destructive interference. Because there are so many of these lines in the diffraction grating, the second you move off that, you're going to be able to find two of them that cancel each other out completely. And so it just immediately goes to 0. Okay, so that's some wave stuff. Do you have any tips on spotting similar angles? I had a question on finding an expression for an electron's trajectory as a function of position of time. It was hard to spot. How would I spot similar triangles? Well, It's certainly easy whenever you have a sort of slope situation, or whenever you see kind of two different orientations of your axes, right? So in this one, you have the sort of diagonal orientation where you have things going parallel and perpendicular to the plane, or you have things in this kind of vertical horizontal plane. And in this sense, you see the same sorts of angles everywhere. And wherever you see the same sorts of angles everywhere, that's when you start to see these similar triangles. By the way, a good technique for if you're really ever getting lost is if you draw your kind of full cross, if that is theta, then they alternate round. 90 minus theta, this becomes theta, this is 90 minus theta, this is theta, this is 90 minus theta, etc. And so because these same angles tend to fall out, wherever you see these same angles, you start to see similar triangles. So one place you might see that, for instance, is in coordinate geometry. If you have that, and then you want the shortest distance to that line, for instance, that becomes a right triangle. As soon as that's theta, well, that's 90 minus theta. Then this is a right angle, which means that this is theta, and that's 90 minus theta because it's shortest distance, so it's perpendicular. And then this becomes 90 minus theta. So you immediately see we have this big triangle has theta and 90 minus theta. This triangle has theta and 90 minus theta. And this triangle has theta and 90 minus theta. So they are all similar. So that's what I would do, is I would start looking for angles, and if anything seems the same, and that would give an indication of similarity. Tangent in a magnetic field in circular motion. So we're talking about a magnetic field. If we're talking about an electron undergoing circular motion, we know the equation you might not know yet by this point in your syllabus is F equals BQV, which is the force on a charged particle moving in an electric field. We then know from Fleming's left-hand rule that if the magnetic field is perpendicular to the direction of motion of the charged particle, then the direction of that force will be perpendicular to both the field and the direction of the motion of the charged particle. Now, what that means is that the force is always acting always acting at right angles to the velocity, which means it is acting towards the center of a circle, and you get circular motion, where this force is mv squared over r. You can rearrange that for r equals mv over bq. Circular motion, that force acts towards the circle. And tangent, I suppose that would be the velocity vector. I'm not quite sure what specific question they could ask that would do something like that. Okay. So let me go back to what I've got now. Yes. Okay, so let's have fun with this. Let's imagine. Actually, I'll do one other sort of explaining sort of from the syllabus stuff. I find that people sometimes don't have the best grasp of the more like qualitative side of physics. So things like why convection currents arise in a very thorough, rigorous process. Because people often are very, very confident with equations, maybe less so with some of the qualitative descriptors. So how I would handle that, as you have a flame or some sort of heat source, it heats the air around it. I will demonstrate this with diagrams. That makes sense for visual learners. That's poor flame. Bad flame. Flame. So let's imagine I've got a candle, right? What's happening here is I'm heating the air around the flame. And I know as I heat a gas, it expands. If you want to stick an equation in that, PV equals nRT. We know atmospheric pressure is maintained. As I increase the temperature, I increase the volume. So it expands. I also know that density is mass over volume. The mass is the same because it's the same amount of air. It's the same molecules of air. So the same mass over a larger volume means that the density decreases. Because the density decreases, we know that the warmer air then floats on top of the colder air. So it rises. As it loses its heat energy to the surroundings, it then, by the same logic, condenses. Not condenses, but it contracts and then becomes denser and then falls again. And so that is where these convection currents come from. But that process of this, therefore this, therefore this, therefore this, it's actually very similar to doing mathematical proof, just with concepts. Right? Don't let yourself move on until you're completely satisfied that every step follows on rigorously from the step right before. And then I think the final thing I had on the agenda is, do I want to save that for interview? I did want to save that one for interview. I'm going to save that one. I'll do that one next week because I'm definitely going to use that question. It's kind of a classic. So I'll hold off on that one, but instead we'll talk about rainbows. If we're going to stick to the qualitative, let's stick to the qualitative. So question might be something general like, why do we see rainbows? Sticking on the waves part of physics. Where does a rainbow come from? We know this is dispersion of light. So this is similar to when you have the prism, white light comes in and then it gets refracted. The refractive index is different for different wavelengths of light, and that causes it to spread out in a rainbow. Now, look what I just did, by the way. Very important skill this. Did I just answer the question of where rainbows come from? Nope. What I did was I took it and brought it back to the syllabus where I know I can talk about something with confidence. And I made that my start point. Similar to when you talk about how to do mathematical proof, you have to start from something that is mathematically true. Like something, the bracket squared is bigger than or equal to 0. It has to be your start point, and then you lead forward to the intended target. I just did that. I went, okay, I don't know about that, but let me take it to what I do know. I know dispersion's true, so I'm going to start there and then bring it to the question you just asked. So I know that's true. And so the question becomes, okay, well, the same thing must be happening in the water. This happens after it rains. There are water droplets in the air. So the light goes into the water droplets. And similarly, because of their shape, they are the prism happens because these two sides that it goes through are not parallel. In a glass block, the light recombines and goes parallel to like where it was originally, but that is not the shape that a water droplet has. It's more similar to this as that gets really big. And so we get that same dispersion effect. It splits the light out, and then it's sort of, we see a rainbow. Okay, cool. So the question then might be, great, I've got my rainbow. It actually helps if I share my screen so you can see it. And I'm realizing I'm running up over time, so I'll probably make this the last one. But the question then becomes, is the red going to be here, or is the red going to be on the outside, or is the red going to be on the inside? You might know from your day-to-day that the red is going to be on the outside, but then the question becomes why? And again, I would drag that back to the syllabus. and say something like the red light has a higher wavelength. It is diffracted less, or sorry, refracted less, and the violet light is refracted more. Or actually, is this diffraction? Because I could also demonstrate what else I know from the syllabus, which is that if I was sending red light through a double slit, then it might be diffraction. Yeah, no, sorry, it is diffraction, not refraction. Okay, so diffraction, I know if I'm sending light through a single slit, I'm going to get these fringes, right? I'm going to get a central bright fringe, and then I'm going to get other fringes on the outside. And I know that the higher the wavelength, the more spread out those fringes will be. And so I would expect red to be spread out further than violet is. And that happens on this side as well. And that happens in a spherical aperture. So it arcs up like that and you get a rainbow. So hopefully that makes a bit of sense of some of the ways to tie questions to syllabus material. Start from syllabus material, start from a place of comfort, and apply it to the question at hand. Some of those syllabus points, get really good at your SUVATs, get really good at your electricity laws, know your gas laws, energy considerations, know how to handle friction, know how to handle graphs. Like anything that's in the syllabus, anything that's for ESAT, make sure you're good and ready for it. Because that's the kind of stuff that'll really upset you if you don't get it in the moment. It'll make you feel like you haven't shown your best work. So that would be my piece of advice for this week. Next week, we're going to do what's likely to be the final one in our pre-interview series, where I'm going to just empty the tank with all of what I think the really good questions are. So feel free to tune into that. And feel free to bring in any last questions you have that you want to put to me to see how I handle them. So with that, I'm going to leave you. Work hard, have fun this week. And now that all of you actually got your interview offers, use a website for questions. I'm going to filibuster until I get that, because that sounds like it's going to be a good resource. So I'm going to filibuster. So I hope you all have a good week. I hope you all... Oh, and by the way, actually, let's have a final talk about... So I've spoken a lot. It's a bit difficult for me to do this as well as like demonstration, but thinking about how you emotionally handle the interaction. So I am doing this sort of direct to camera. I can't get any feedback from you apart from in a chat, but in an actual interview situation, you might be expecting a bit more of a back and forth with them. Be prepared for them to be very, very stony-faced with you and to give you nothing so as not to interfere with it, to give you the space to play with the ideas on your own and see what you can do independently, which might feel weird with a person sitting staring at you. You feel like they should be speaking to you and they don't. So it's a bit like, ugh. But yeah, sort of, if you can in your mock interview, see if you can think about making it less about being seen by someone. And it's not really about you, it's about the science in between you. So I'm just holding out. So it seems like I'm going to get a good website in the chat. So I will hold out for a bit while I wait for that. Old Russian questions. And I feel like the Russians would know what they're doing. So let me think about other ways to filibuster while I wait for that website to come through. Savchenko solutions. Let me have a quick cheeky little Google of that now and see if that's Sav. Love a good resource. Ooh. I have not heard of this. So it does seem legit. So I'll share it. it's not got all the work solutions. So just kind of sharing, this is what's coming up. Someone in the chat. This website, Savchenko Solutions. It seems to have different websites. Oh, sorry, different styles of question that you can put yourself to. Okay, I'll have a look at this and see if it's good. So thank you for that. That's super helpful. Now, get yourself off. Sorry, what? Let me get to... I swear I don't mean to come out with these things. My students absolutely roast me for accidentally walking into these things. So yeah. Have yourself a nice evening. Work hard. Have fun. I'll see you guys next time.